Calculus is an area of mathematics that is part of every science degree. The tools it offers for precision, prediction, and approximation are undoubtedly one of the most valuable resources for students. Concepts such as limits and continuity become cornerstones to every procedure. However, rigorous definitions are often hidden from students from every branch of science, that being biologists, physicists, and engineers, and even when taught, they don't feel intuitive to the majority of them. That's why, in order to cover such a gap in rigor, students have the need to use flawed intuitions, like drawing it without lifting the pencil, or taking the limit as the point where it seems to approach from a graphic representation. Such a vision of the concepts not only is incomplete, but prevents us from exploring many more behaviors which lay hidden beneath the belief our eyes are good at spotting tendencies. The purpose of this video will be to give a motivated and full of questions travel into the ideas surrounding predictability, trying to give the viewers the feeling it could have been they the ones to come up with such ideas. It is also important to mention this video assumes nearly no mathematical background, as it is the intention a high school student could be capable of understanding the concepts. And although we will build up rigor, we won't use formal language until the very end, where hopefully the epsilon-delta definitions will seem like a good old friend. That said, let's get started. So let's imagine we were one of those people who go everywhere with a camera. As it turns out, we are great fans of watching our videos, so we constantly take a look at a couple. However, it's not always so easy to know what happens since our camera has a little flaw. There's always a time around the middle where the image goes blank. Usually, we take no interest in such matters, but today, while watching the video of our little cousin's party, something caught our attention. In the video, there was a part where there came a piñata. You know, the thing that's tied to a rope and is pulled up and down until someone hits it and breaks free all of the candies within. While watching the scene, we couldn't help to notice the kid currently trying to hit it missed his shot. Unfortunately, the moment of the strike was precisely on the spot where our camera goes blank, so we couldn't see where the piñata was at that moment. Out of curiosity, we wonder, where was it? Of course, we can't immediately know because that piece is missing from our recording, but nevertheless, the idea pops into our mind. Could we predict it? If so, what could be a good strategy to know its position? Perhaps it would be easier if we knew both where it was and where it went. Watching both the past and future sure sounds like a good idea to start to capture the feeling of the piñata's behavior. So in order to have a way to compare its positions, we'll say the lowest position the piñata can go is high 0, and the highest position is high 100. Thus, moving the video on our camera, we decide to take a look at the positions it had 4 seconds before and after the blank moment, for which we get positions 8 and 0 respectively. So right now, it might seem like a good idea to suppose the piñata would be somewhere between those two positions at the blank moment. That is somewhere between 8 and 0, even probably 4 some would say, but maybe we're wrong. In the end, many things can happen in a 4-second period. Why don't we zoom in on time and see where it was 3 seconds before and after the blank moment? It appears we were wrong. Clearly, the position we want should be between 10 and 30, so perhaps the right prediction is 20. But again, many things could happen in 3 seconds. Why don't we see the period for 2? Now it seems the position must be between 30 and 100. Is 65 the right prediction? The positions again changed drastically, and we don't seem to get closer to predicting anything. But maybe the issue is that we aren't seeing close enough. 2 seconds is still a lot of distance apart from the blank moment. Maybe when we see the piñata at closer times, its behavior will be easier to deduce. Let's see if we find something as we shrink the time window in which we look. So we take a time window of 1.5 seconds. And we look closer. and closer. Each time getting nearer and nearer to time zero. Finally, as we shrunk the time window, it appears the piñata is closer and closer to being in position 60. But is this true? Maybe it is just as before, and out of the blue, when we zoom in for a time window of 0.0001 seconds, we'll have the piñata's positions have once again changed drastically. At what point can we say we've seen enough? When will our time window be so small that we leave no room for further change? Think about it. No matter how small the amount of time we see in the past and future, we are always gonna leave time. The piñata will always have time to make a change, even if the time we left was a nanosecond. In that interval, it could have moved way up or way down, tearing our prediction apart. No matter what size for the window we choose, it will always have the possibility for drastic change. So clearly, this strategy isn't gonna work and turns out inadequate to find the prediction. We may see some pattern that hints to a particular value, but ultimately there will always be a part of the scene we haven't looked into yet, and there could be a change. Thus, looking at the particular positions of the piñata near the blank moment can't possibly tell us what the prediction is. However, we do get something out of this approach. 60 did seem like a good prediction. It kind of seemed as if the more we closed in our time window, the closer the piñata also got to 60, and it truly seemed it would stay there. But as we know, this thought may be wrong, and suddenly, boom, it's moved elsewhere. Nevertheless, we have strong reasons to suspect 60 is a possible right prediction. Well, supposing three cases can be called strong reasons, but we are used to concluding behaviors from a very small amount of reassuring samples. So, it may be we are incapable to discover which is the prediction, but would it perhaps be easier to check if a guess, such as 60, is right or wrong? If it was the case 60 truly was the position the piñata ultimately moved to at the blank moment, what would have needed to happen? What does 60 need to satisfy if it was our true prediction? What makes a guess a possible prediction? Notice, assuming 60 is already the position the piñata has at the blank moment, allows us to think backward. If it is at 60, then that means somehow it must have got there, right? Since it can magically appear at the spot it needed to move there. Therefore, there must have been a moment when it entered position 60, that is, was moving with the clear intention of reaching 60. Of course, it can go up, down, lay steady, but at the end, since it reaches 60 at the blank moment, it must necessarily be there is a time when it gets there. There must have been a moment where it was so, but so immensely close to reaching 60. And the same goes for the future. If the piñata was at position 60, then there must be a moment when it leaves it. That is, there must be a time when we see it get very, very little away from 60 because it's just getting out. However, this word we used, close, what does it mean? When we say there must be some moment where it is immensely close, what are we referring to? Let's ground that idea. So as we said, because the piñata must be at position 60 at the blank moment, then at some point before the blank moment, it must go towards 60. So for example, clearly, there must be a time when it stops going up and down and gets nearer than 10 units away from 60. This is due to the fact that to get to 60, it is necessary to go from a 10 unit away distance to a 0 unit away distance. Thus, there must be a time before the blank moment from which there onward we are no farther than 10 units away. But again, because we ultimately reach 60, there must be a time before the blank moment from which there onward we are nearer than 1 unit away. Again, because if we reach 60, then we must necessarily go from 1 unit away distance to a 0 unit away distance. Thus such time must exist. And so on, we can repeat the same argument for any distance that we like, because if we reach 60, then we must, at some point before the blank moment, get nearer than any distance to ultimately reach it. In the same way, the idea replicates for the future positions. If we were at 60 at the blank moment, then there must be a time after it, in which we have not already gotten 10 units away. And that's because to get to 10 units away, we must go from 0 to 10. Similarly, because we were at 60, then for sure there has not only to be a time after the blank moment in which we hadn't got to 10 units away, but there must also exist one in which we haven't gotten 1 unit away. And the same goes for 0.1 units away. This analysis gives us a hint on how to check if 60 truly is the place where the piñata will be at the blank moment. If 60 was the true prediction, then there needs to be a time both before and after the blank moment such that the piñata's position can't be farther than any given distance. This means that to whatever distance we say, as small as it may be, there must always be an interval of time in which the piñata position is no farther than that distance from 60. So in particular, if 60 was the right prediction, then there must be a time interval around the blank moment such that inside the time interval, the piñata's position is no farther than 10 units away from 60 both in the past and future. And there must also be a time interval in which the piñata's positions are no farther than 1 unit away both in the past and future. And also one in which the piñata's positions are no farther than 0.1 units away. And so it must be for every distance, say 1/2, 100 or 1,000,000 units away. For all of them, it must surely be possible to find such a time interval in which the piñata position doesn't go farther. Notice, this strategy of always trapping the distance of the piñata around our guess more and more is what ultimately lets the behavior have no other option than to follow in our prediction. It's like building walls around the behavior and bounding it to close into what we want it to be. So, having thought of these ideas surrounding the notion of prediction makes us question, what else can we predict? Not wanting to waste more time thinking about piñatas and being excited of our new ability, we start to test it in different scenarios. And of course, we turn to an issue of the highest importance. We want our crush to notice us. Our plan is the following. We want to discreetly bump into our crush in the hallway just as we leave our classroom and our crush is walking past it. For this, we have already used the only opportunity to skip classes we had in order to record the path it takes to go from its class to the end of the hall. However, just as our crush was going to walk in front of our classroom, the video went blank. Because of that missing detail, which is key to making it look natural and make it work, we hadn't yet dared to execute our plan, but perhaps now we have a chance. The time of action, which is where our video went blank, happens exactly 10 seconds after our crush has left his class. Also, by neat observation, we have noticed our crush usually walks at a constant speed, which happens to be 2 meters per second. This happened to also be the case in our video, and we know for a fact our crush always travels the hall in the same way. So, can we predict where it would be? Taking a look at different time windows in our video, we have the following. Notice these time window diagrams are useful, but not so enlightening, because we are only seeing a couple of states at a time. Wouldn't it be better if we were able to see a bunch of them at once? It's from here we get the incredible idea to graph them all in the same space in order to see the bigger picture. The diagram we'll choose will conveniently allow us to relate times with positions. It's important to notice, in this kind of diagram, Our time windows can be seen as equidistant points to the mark of 10 seconds, and it gives us a neater visualization of the action of closing in on time 10. The same information placed on a table looks like. Here we start to guess maybe the prediction will be being at the 20th meter when 10 seconds pass. However, we have to remember this is just a guess. Here we might convince ourselves it must be the case 20 will be the true answer because it always moves 2 meters per second. But the issue lies in the fact that information only applies to the moments we see in the video, of which the 10-second moment is not a part of. It is not at all obvious how will we know our crush was there, given that we don't actually know where our crush is at that instant. Maybe out of the blue it decided to change course or start to walk faster or slower and then take the pace again. You see, although it might seem simple and trivial, the actual way to know for sure is not trivial at all. Also, when we graph all of our information on the table, we might be tempted to join them with a line, and therefore make the clever argument it sure looks like at the time of 10 seconds the drawing should continue with our crush being at position 20. However, here we are making what could be a critical mistake, which is encouraged by our drawing. Notice that although in our graph the positions seem to be arranged in a straight continuous line, we ask ourselves, how did we know the drawing took such a shape? And the answer is, we didn't. In the end, we were only able to ask for a finite number of windows of time and draw them. But in between each moment, we could have asked for another that we left unchecked. For example, we didn't ask for the time window of 5 seconds in our table, so how did we know we could draw time 5 as if it was in position 10? What if in the time window of 0.001 seconds, our crush was suddenly at position 100? Of course, we can check it. But then, what about the time windows of 0.00001 seconds and 0.00001 seconds? We have come back to the issue we previously encountered. To see where the behavior leads, we would have to ask for infinitely many time windows, every time smaller and smaller, never being able to finish the search for the unexpected. Drawing the line connecting the points assumes we can ask for infinitely many points, which sadly is not our case, but thankfully we now know our way out. By the finite information we have seen, we have already gotten the idea, of course at 10 seconds the behavior should lead to position 20. So let's show our guess. This means, for any distance away from 20, there must be some time interval in which our crush is not farther away. So in particular, if 20 was the right prediction, then surely there will be a time interval when our crush is closer than 2 units away. To find that interval, notice we need to find a time period in which the positions are trapped between positions 18 and 22. In order to work it out, we must answer the question, for what times is the position past 18 but also before 22? Notice in order to figure out the first part, if we ask for the positions of our crush at any time past 9, since the positions are always twice the time, then the position will be greater than 18. Similarly, we can notice if we ask for the positions of our crush at any time before 11, then the position would be smaller than 22. This means that if we take the time interval from 9 to 11, which is the same as to say the interval of 1 second around 10, then all of the positions within the interval will be no farther than 2 units away from 20. Notice the huge difference between this strategy and the other is that we didn't need to check infinite time windows, but instead argued that if the positions needed to be bounded by some distance, then the times must also be bounded. It's more of a global behavior argument than an argument which goes point by point. We don't know what the position values are for times in the interval, but we know they are trapped, and that makes the whole difference. It doesn't matter if we don't evaluate all. Following our strategy, notice if we now wanted to find a time interval in which our crush was closer than 0.02 units away from 20, then applying the same reasoning, if we took times after 9.99, then we will have positions after 19.98. And if we took times before 10.01, then we will have positions before 20.02. Thus, if we took the time interval of 0.01 seconds around 10, then all of the positions within would be no farther than 0.2 units away from 20. As a matter of fact, those distances weren't special. This argument can be used for any distance epsilon that we want. Take any value for epsilon. Then, because distances of time are getting doubled, we can already expect that if we take times epsilon over 2 units away from 10, then that difference will be expanded to a distance of epsilon units away from position 20. Thus, no matter the distance, we can always find an interval of time around 10 in which the positions of our crush are no farther. With this, we can conclude 20 is the prediction or expected position at time 10. Now, in this case, we were successful because our supposed guess was right. But what would have happened if we had guessed wrongly? Say we thought 14 was the expected value. What exactly goes wrong when we try to show it is? Well, because 14 really isn't, there must be a point where a crush doesn't get closer to 14 because it never really gets there. That is, there must be some distance from 14 that our crush will never get as close as, no matter in which time interval around 10 we are looking. With the help once again of some finite number of positions for our crush, we can give ourselves the idea it will never be the case it gets as close as 2 units from 14. In order to show this, we only need to argue that no matter the time period we are looking into, there is always some moment where a crush didn't stay close enough. That is, a moment where it went farther away from 14. In other words, this means there is no time period in which we can say it was entirely that close to 14. So let's take any distance away from 10 seconds, say 1. Notice any position our crush took inside the interval is farther away than 2 units from 14. Thus we can take any as a counterexample, say 9, which has position 18 and is 4 units away from 14. But notice, our argument had nothing special, and no matter what interval we took away from 10, there will always be a point in the interval which is above the 2-unit line mark from 14. Take for example any distance bigger than 1, then we already know time 9 goes farther. On the other hand, take any distance smaller than 1, and we have in that interval any point will work because if the times are greater than 9, then the positions are greater than 18. Therefore, there is no time interval such that our crush stays closer than 2 units from 14. Hence, 14 can possibly be our expected value. Having aced our prediction and managed to get us a date, we can already see it will always be the case our prediction is right, because changes must follow a rhythm, or a flow. There must be a kind of transition from one state to another. And with the strategy of analysis, we're being able to follow it and thus predict it. But as we get a smile on our faces, the doubt falls upon us. Things cannot pop and vanish suddenly, can they? Could we still predict even if things change suddenly? As an answer to our question, we come across a peculiar event in our own houses. Our light bulb is flickering. We decide to record the behavior and examine the video. As we start to watch it, we see the light bulb is on, but unexpectedly, it goes off. Our greatest fears are confirmed. Its behavior can pop and vanish without previous notice. As we continue watching, we can see the light bulb state goes from on to off alternatively, always changing from one to another, and suddenly the video goes blank at the 3-second mark, and it continues in the same manner. How are we going to predict such a behavior if from one state to another there is no transition whatsoever that indicates us any intention of going where it went? It seems as if our strategy will crumble. All of its idea was based on the fact there was a moment when we entered and left. But if it isn't anymore the case we have to enter or leave a state, and we can simply appear, then it could be that we are left with no choice and such behaviors are unpredictable. Using our previous technique to visualize its behavior, we can take the horizontal axis to be the time and the vertical axis to be the intensity of the light, where 1 will represent on and 0 off. So which is it? Will it be on or off? No matter the time interval we choose, its state is always still going from top to bottom abruptly. Notice, using our strategy and investigating the behavior, we can say that if it was the case on was the expected value, then it should satisfy that there is a time interval in which we are getting closer to being on state 1. But that's not true, because no matter the time interval we choose, there will always be a moment in between when the light bulb was off. Similarly, if we thought off was the expected value, no matter the time interval, there will always be a moment in which it is on. And so it follows for any prediction we choose, say we guessed it to be in state 1/2. Now, no matter the interval we choose, we will always have moments where the light bulb is off and moments in which it is on. We're incapable of bounding the behavior around any given value. It always manages to get out of any tight constraint. Therefore, we are left without any clue of what might be the state of the light bulb at 3 seconds. It's unpredictable. It might be on, it might be off, or perhaps nothing at all. The power of appearing at pleasure gives it the power to decide the outcome with complete independence from the previous and posterior actions. Thus it seems reasonable to think in such cases, where there can be sudden jumps, predictability is off the table. However, what made sudden behavior so troubling? Thinking about it, we can notice the most annoying thing wasn't its abruptness, but rather that it happened constantly. Could we perhaps save our prediction ability if it only happened sometimes? Let's look at an example. Take the following recorded behavior. Like last time, since it is a light bulb, it can be suddenly changed of state without previous notice. However, take a look at its behavior. Can we predict it? It appears to be the case it will be off, but how exactly did we know? Wasn't it the case its state went on and off? Well, yes, it did, but different from last time, there was an interval in which it maintained a fluent behavior. And think about it, when we predict things, do we care about the things that happened 2 years ago? It would be funny to think while trying to predict through which door someone will pass, we would have to consider what that person ate a week ago. And don't get me wrong, perhaps it does. Maybe that person is going through the stomach doctor's door and not the leg doctor's door because the food gave him a stomachache. But with our strategy, an important thing we assume, and we often do in so many things in our daily life, is that we believe a decision can be glimpsed moments before the time of action. No matter the reason, surely, if someone was going to go to the stomach doctor's door, then that person must have earlier stood in front and later passed it. Therefore, any sudden or drastic change in behavior isn't of our interest as long as it's possible to look closer, in an interval in which they don't happen anymore. Graphing the state of our light bulb in order to see its global behavior, we can observe indeed, inside the 1 unit interval around 6, every sudden change has been left outside our scope. Now, in order to show our guess is the right prediction, notice given any distance epsilon away from 0, we can always take any interval smaller or equal to the 1 unit interval around 6, and it will satisfy the states of the light bulb remain closer than epsilon to 0, because within, every state is already at 0. It is predictable. So we ask ourselves, will we always be capable of escaping jumps if they don't happen constantly? What made those jumps escapable? As we previously noted, the key ingredient for discarding sudden changes was that at some time interval we could leave them all behind. So, can there be an inescapable jump? That is, could there be a jump that no matter the time interval, it can never be left behind? If that happened, then for sure it must have happened at some time, but due to the fact we can always make the time interval smaller than any time, different from our blank moment, then all of those would be escapable. So it must be it is a time from which we can't get any closer. But the only time which we can't close in more is precisely the blank moment, because it is already 0 seconds away from itself. This means a sudden change just as we pass the blank moment will be inescapable. To see an example, we decide to record another behavior of a light bulb. Can we predict it? As we can see, the problem is we aren't sure if at the 3-second mark it was off and just right after got on, or if precisely at the 3-second mark it turned on. Graphing the states of our light bulb, we can confirm our suspicions. No matter the value we guessed it to be at 3 seconds, then in particular it should be possible to find a time interval around 3 such that all states inside the interval are no farther than half units from our prediction. But no matter the time interval we choose, there will always be states which lie farther away. Thus the behavior isn't predictable. Nevertheless, we are glad at least we saved a case in which we could dodge the effect of sudden change. Well, at least in some sense. Notice, although we managed to make a prediction for the escapable example of our light bulb, due to the fact the light bulb can get on without previous notice, we can have the following scenario. Our predictions can be wrong. It's because of this phenomenon that we see the necessity to classify 3 different cases. The case where the object behaves as we predict, the case where it doesn't behave as we predict, and the case in which there isn't a prediction at all. Paying closer attention to all of our cases and trying to save us the work of our analysis, we might notice that even if we can only graph by showing a finite number of points, if we pretended we could actually draw the whole interval around the time in which our video goes blank, then all of our cases would be unified by a single characteristic, ones that we can draw without lifting our pencils. And others we cannot. Going forward with our thoughts, we can get the idea if it were possible to make a prediction, then it must be the behavior has a fluent and river-like continuous change, at least in some time interval close to the time we go blank. And that if our prediction is right, then the missing value completes the picture to have no bumps. These observations lead us to the incredible conclusion if we had a behavior as if it were drawn without lifting our pencil, at least in an interval, then the behavior would be predictable, and that on the contrary, if we lift the pencil at every interval, or have an inescapable jump, then it wouldn't. As a matter of fact, it's based on this idea that the name continuous is given to a behavior that not only is predictable, but also coincides with the prediction. A drawing without lifting the pencil looks exactly like the concept of fluid change we want to represent. However, although these conjectures appear to save us a lot of work, they are misleading. If a behavior can be predicted, must it be drawn without lifting the pencil? Suppose, for example, we recorded someone playing the piano, and we heard the following tune. What would we predict to be the tune at the 5-second mark? Would it perhaps be or? Graphing the global behavior, we have the following. By inspection of the graph, in which greater values for the tone are lower sounds, we can confirm the guess is the right prediction, because no matter the distance of the tone, there is always an interval in time in which the sound is no lower. This example reinforces our theory that something predictable doesn't have jumps, and can be tackled by pretending we can draw all states. But how about? Can we predict it? Yes, we can. It seems as if the tone was dropping and the pitch at 3 seconds would be. In fact, by graphing the states of the sound, we can clearly observe there is a tendency of the values to fall. Applying our test for predictions, we can see indeed, given any distance of the tone, there is always an interval in time in which the tone is no lower. It is predictable, and if we discovered in fact at time 3 the tone was our guess, then the behavior would also be continuous. But what happened? Didn't we say it needed to be drawn without lifting the pencil? What about the jumps? This behavior jumps everywhere. Nevertheless, we can predict it. Where did our intuition go wrong? Before we try to answer what went wrong, perhaps it's best to first narrow down what exactly did we mean by something drawn without lifting the pencil. Of course, we think we know what it means when we use our sight, but what exactly do we look for to know something is and something else isn't? Which are the properties that a behavior needs to have in order to tell it to us drawn without lifting the pencil? Maybe the two main properties that come to mind are having no blank spaces and somehow having a way to tell from a position which one needs to be the next position in order for it to remain drawn without lifting the pencil. However, this last condition is extremely hard. Suppose we knew the following behavior was drawn without lifting our pencil, and that it must continue that way until we reach the position marked at time 6. Because our drawing stops at time 4, and we must continue drawing, since time 6 is separated from time 4, what positions are we allowed to visit in the interval between so that we don't break its not lifting rule? In particular, because we must be somewhere at time 5, since we can't have blank spaces, why don't we choose some arbitrary position to be in? Did we break a rule? No, in fact not, because we still have time between 4 and 5 to join them, and time between 5 and 6 to join them as well. So at time 5, any position can be achieved, and it doesn't conflict with our must be drawn without lifting the pencil restriction. Repeating the process, we could now ask the same question, again and again, because every position we say will still be separated from time 4. And by the same reasoning, it follows that every time in between we could have been anywhere we liked. Wait a minute. Anywhere we want at any time? Yes, no matter the position we choose for the behavior, since it is not at time 4, we'll always have time in between to join them. But does that mean we can be randomly dotted at any interval of time around time 4? Yes, always with the promise in the time in between it will be joined. And since we can perform such an argument in smaller and smaller intervals of time, this amounts to having jumps constantly happening after time 4. And how do we check if they actually join in the space in between? Well, because that space can get smaller and smaller each time we perform the argument, it would follow we would need to check the values at the infinite number of times which happen in between. But once again, we stumble upon the same issue as earlier. We can't possibly check an infinitely amount of values or states, even if there were. If we come to think about it, even when in our screens we see a line, really, when we zoom in, we can realize it's just a bunch of dots with spaces in between, since the screen is made of pixels and we can have something in between 2 pixels. It's the resolution, or in other words, the smallness of those points which on a large scale produce the illusion. However, although we can check an infinite number of times, we still believe with our sight we can distinguish whether some drawing was done without lifting the pencil or not. What is the trick? The trick is precisely what we came to as our solution to overcome such impotence. The key is closeness. We don't know if things are joining up the way they are supposed to, because we can't see beyond certain resolution, but we can get a feel for the way the positions start to accumulate around a given time, and that is our strategy. Yes, the positions can be anywhere at any time, but in order to follow a drawn without lifting the pencil behavior, it must be at some time interval around time 4. They must not be very far away because our pencil can't go too far away. We expect, as we look closer in time, the positions will also begin to approach the point where we stop to draw. It's precisely because of the fact we were never really dealing with a behavior that could be drawn without lifting the pencil, at least not in our thought process, that our strategy focused on a way to encapsulate the idea of closeness without the need to say anything particular for each individual state. Reflecting upon our strategy to predict behaviors, we can see the only thing we asked for was that the states or values started to be trapped closer and closer to our guess, never really saying anything about their arrangement or occurrence in the bounded region, because doing so would imply we actually know them individually. Jumps were never really the issue. No, the problem wasn't jumps. The problem was some jumps didn't get as close as we wanted. The issue was never continuity in the sense in which we imagine a curve. It was tendency and the forecast of the expected. And the secret for those, as we chose it to be, was closeness. Our analysis is a strategy of approximations. The only thing necessary to make a prediction is closeness, and for that, we only need unending resolution, the capability to always look closer. Carrying on with our reflection, even the idea of not having blank spaces, that is, having values or states at every time, is irrelevant for our prediction capacity. Suppose, for example, we recorded the throw of a rock on a lake, those throws in which the rock makes jumps on the surface, and that we recorded it at ground level. That being, in our video we cannot see the stone in the air, just the places where it hits the water. Can we predict where it will sink? Yes, of course we can. We get the feeling the rock's position closest in to sink at 5 meters away from the shore. Graphing the positions of the rock to see its global behavior, we can confirm that no matter how close we ask the behavior to grab around position 5, there is always an interval in time around the 3-second mark in which the rock goes no farther. Indeed, it is predictable. And the astonishing thing about such an example is that we didn't even care the rock disappeared in whole intervals of time, or even that it never reappeared after the 3-second mark. The way we can think about it is similar to the way we would follow the footsteps of an animal in the woods. Even if in between each footstep there isn't any other, the only relevant condition so that we don't lose track is that someplace ahead we can see another. This translated to our problem means that no matter the time interval we are in, if the behavior is predictable, then there must at least be one state or value for the behavior on such interval. Notice such a condition has implicitly integrated the unending resolution needed for closeness, because once we have the value guaranteed to be inside our time interval, we can shrink it until we lose it, and because there must at least be one in every interval, then we need another in this one, and again, creating the effect of an infinite track of footsteps as we close the time interval. This is the necessary condition to follow the animal, or in this case behavior, an endless path of clues. Notice in the case there's not, we will have something like this, where at some time period we will be clueless of where to go next, because we lack information to tell any tendency of the behavior at all. So all this said, we can now for sure say being able to make a prediction, and in fact predicting a behavior, doesn't have anything to do with the dark concept of drawing it without lifting the pencil, which was a final attempt to save the information provided by our sight, so hardwired into our brains to give the impression of fluid transitions, while on a closer look, everything turns out dotted. Now we can clearly see that when at the start we thought of the piñata entering and going out of the predicted value, our visual understanding was flawed, and really was meant in a much broader and richer sense of change, of what truly means to approach a state. Up to this point, we have strengthened our concept of what is predictable, coming from the problem of how could we predict the position of a piñata, to having actually developed an idea that encapsulates predictability with independence of our ability to see the whole. Beyond the deeper understanding of the topic, what we want the viewer to get out of this video is the feeling that mathematics and its ideas aren't something that's popped out of the blue, and that definitions, as well as results, aren't inventions disconnected from experimental thought. As Francisco Vera points out, mathematics as a collection of ideas is a museum of dead things. What we wanted to show was the process, the creative and detective-like process behind the birth and discovery of an idea. Answers alone don't involve us in any way. They turn us into mere spectators, and therefore give us the bitter sensation that we could never understand such a concept, and that such problems escape us, but it's the questions, even more than the answers, the ones that bring sense and life to a problem. With this approach, we want to show achieving rigor isn't something abstract that only mathematicians can understand or must care about, and that rigor is built upon the unending current of questions surrounding the big question: how do we know it? The purpose of rigor isn't to annihilate intuition, but on the contrary, to enforce it and find its cracks until our intuition corresponds to the why of the concept and its flaws to the why not. Intuition is always necessary. We only need to distinguish the right from the wrong. We will now briefly display the concepts work in the video, followed by the names and formal statements we often see in books.